Okay, so my demonstration for second law, we need to first draw the diagram. So this is a setup, diagram of the setup. That's our stand. Here is the ramp. On the ramp, we have the cart. Okay, this right here is the bolt that goes through the cart and attaches it to the ramp so it doesn't fall off the ramp. Okay, now attached to that cart is a string, and that string goes up over the pulley and comes down, and on the other end of that string we have a few plates in there that provide the pull that pulls the cart up the track. Okay? So the cart, right there, when we're talking about Newton's second law, we have force, mass, and acceleration. All right, 3 variables. The cart, we can vary its mass. So the mass of the cart represents the mass in the formula. The plates here that are on the other end of the string that are pulling down, okay, that represents the force in the formula. Now the acceleration, as this cart goes up the ramp, it will accelerate. So, accelerates up ramp. Okay? So there is your mass, your acceleration, and your force. Okay? Our 3 variables. Can you guys see the diagram well enough to draw it?
Not really.
Pedro, can you hit the light real fast? Thank you. Okay, so no fancy art, just make sure you understand what's going on. You see the picture and you'll remember this a month or 2 from now. Okay? All right, now, when we do this setup, we are going to be altering some variables. We're going to be doing some controls to some variables. In science, when we are talking about doing an experiment, we have what are called independent and dependent variables. Okay? Independent and dependent variables. Does that sound familiar to anybody? Okay. Hopefully that sounds familiar. That's good. Okay. For the first experiment, we are going to set up here, write down constant force. Okay? One of our variables we're going to hold constant, and the first one we're going to hold constant is force. Okay? With the force held constant, I'm going to have an independent variable and I'm going to have a dependent variable. Okay, the independent variable is something that I can control, that I can adjust, that I can change, that I can manipulate. Okay? If this force is going to remain constant, I can change or adjust the mass on the cart. Okay? So the mass of the cart. That's going to be my independent variable. My dependent variable is going to depend on that independent variable. So, as I change the mass of the cart and the force is held constant, the acceleration will change. Okay? So the acceleration of the cart will be the dependent variable because it will change as I change the independent variable. Or at least it should. Okay? So that is the setup on the journal to get started. Cool? Alright. Here's our setup. We have the cart. We have the force, the plates on the end of the string, which are going to provide the force that brings the cart up the ramp. Okay? And the plates that we can add on to the cart to change its mass. We'll start with larger mass. We'll put 2 plates on.
That's 2 plates?
Yep, 2 plates. These plates are made of steel, so they're kind of heavy. So even though it doesn't look like much, it's actually quite a bit of mass I add to it. Alright, so we're going to start off with a larger mass. There. Okay? Observe the motion of the cart.
It goes up slower.
Yeah.
Okay, it goes up. Alright? Now, think about what we know about motion. Concepts. Okay, there's constant velocity, there's acceleration, there's deceleration, and your eyes just say it's moving, right? Because our eyes are not very accurate. So, I want you to use your ears. Listen to it go up the track.
Acceleration.
Do you guys hear that acceleration? Listen again. Do you go the donk? Alright? So you're actually listening to the wheels. You're hearing the friction in the wheels as they turn, and you hear the wheel turning faster and faster and faster.
Yeah.
Alright? You guys hear that? Okay. Now, plates off. So I've now decreased the mass. I have less mass. The force is still the same. Will the acceleration change?
Yeah.
Okay. So, observe.
Really fast.
Okay? It goes really fast, and your eyes say, ooh, really fast. Now, listen to it. Do you hear it accelerate?
Yes.
You do. But you hear it get to you hear it accelerate much, much faster. So you listen to it one more time. Okay? So it happens really, really fast. In less than a second, it gets all the way up the ramp. Okay, so when we had a large mass, okay, when the cart had a large mass, what was the resulting, our independent variable was a large mass, the force was constant, so when we have a large mass, the dependent variable, what was the result of that?
Acceleration.
All right? It was a slow acceleration. Large mass results in a slow acceleration. All right? We also did a small mass when I took the plates off the cart. When we have a small mass, what's the result? We get a fast acceleration. All right, when that little cart doesn't have anything on it, we get a fast acceleration. Okay, now I want to draw this formula in a visual way. Okay? So in this setup, the force was held constant. Next to each one of these, I want you to draw an uppercase F, and we want them both to be the same size. Okay? The force was the same in both scenarios. Okay? However, in this one we had a large mass. So I want you to draw a lowercase m, but I want you to draw it big. Draw a big lowercase m for a large mass, to represent a large mass. Okay? The 2 plates on the cart. When that happens, what's the effect of the acceleration? How does that affect the acceleration?
Smaller.
A slow acceleration or a small acceleration. So I want you to draw a small lowercase a. Okay? Now, again, same scenario, the second scenario, the same force, but this time a small mass. So I want you to draw a small lowercase m. And the result? Fast acceleration, so I want you to draw a large lowercase a. Okay, so you can see in this, if the mass is large, the acceleration is small. If the mass is small, the acceleration is large. Now, from before spring break, when we were talking about Newton's second law, how do we describe that type of relationship? If one's big, the other one's small, and if one's small, the other one's big. How do we describe that sort of relationship? Look at your notes on page 23. Look at your notes on page 23. Everybody, turn your journal to page 23. All right? When one increases and the other one decreases and vice versa, that's called inversely proportional. So, here we just proved, right there with the demonstration, that mass and acceleration are inversely proportional. Mass and acceleration are inversely proportional. All right? Squiggly line. Now we're going to change it up. We're going to readjust our variables. Okay? Now we are going to have a constant mass. We're going to set the cart with 2 plates and leave it at 2 plates. My independent variable. The thing that I can adjust, that I can change, that I can manipulate, that I can alter. What's going to be my independent variable, or what would be an independent variable that I can change or control? If the mass is constant. So look at the setup. If my mass right here is constant, what can I change? Can I change the acceleration or can I change the force? I can change the force. All right? So the force applied is what we say. Okay? The force applied. So my dependent variable, the thing that will automatically change as I adjust my independent variable. So as I adjust the force, the mass is held constant. The thing that's going to automatically change? The acceleration of the cart. Okay? Okay, now we have 2 plates attached to the cart, and we're going to leave it at 2 plates. Okay, that's going to be our constant. Because we can't tell the cart at what rate to accelerate, the only variable else we can change is the force. Okay? So this is going to be the constant mass with a small force. Okay? So observe the movement of the car.
Didn't we already do that one?
We did. Okay? So, thinking again about the observation, what do we observe?
Slow acceleration.
It's a slow acceleration, right? It speeds up, but it does so slowly. Alright? Now, we're going to leave the mass as a constant. We're going to increase the force. I'm going to add 2 more plates onto my 3 plates here that are for applying force. Okay? So I've now increased the force. Okay? Observe.
It's like the first one without the weight, isn't it? Like the first.
So, the mass is held constant, but we have increased the force.
Damn.
Does it accelerate?
Yeah.
Listen to it, hear it. That's an acceleration, right? It goes faster and faster and faster. But what's the difference between the 2 different forces?
Accelerates faster.
It accelerates faster when you have more force. Okay, so first we started off in this situation with the constant mass and a small force. Okay, so with a constant mass and a small force, my independent variable in force, the dependent variable, the resulting acceleration was what?
Slow.
A slow acceleration. Okay? Now again, constant mass, when I have a large force, okay, I increased those dangling plates from 3 to 5. I added 2 more dangling plates, so I increased the force. What was the result on the acceleration?
Fast.
We ended up with a fast acceleration. Okay? So, in this situation, so we're going to draw those formulas again with that relative size thing like we did up here. Okay? Like we did here. This, honestly, to me, doesn't make much sense. But for some people, that visual makes all the sense in the world. Okay? So that's why I do that. Alright, so small force, slow acceleration. So the F, draw a small uppercase F. Okay? On this one we want a large force, so draw a large uppercase F. Okay? So small force, large force. Now, what was held constant? What was the same in both scenarios? The mass. So draw a lowercase m in both of those formulas at the same size. Make sure those m's are the same size. Okay, the mass was held constant. So the mass was the same in both situations. Now, the resulting acceleration with a small force, we get a small acceleration. So draw a small lowercase a. Alright? Large force results in a fast or a large acceleration. So draw a large large lowercase a. So, with force and acceleration, if the force is small, the acceleration is small. If the force is large, the acceleration is large. How do we describe that sort of relationship? If one is small, the other is small. If force is large, the acceleration is large. Alright, so back to notes. Force and acceleration, one goes up, the other goes up, one goes down, the other goes down. We describe that as proportional. Okay? So, force and acceleration are proportional. And yes, I expect you to learn that vocabulary. Proportional and inversely proportional for the quiz. Quiz will be Thursday. Okay?